Hello everyone, I am Teacher Xie. The unit we are going to talk about today is the principle and use of the input components. We will continue with last week's class. Last week, we explained to the students about the controller to the output part, which is what we refer to as the actuator. For this week, we are going to add the input part so that it becomes a complete control system, which will also be a standard robot structure that we talked about during our first class. Let's take a look at this PowerPoint. You can see that there are two new terms. One is called open loop control system, and the other is called closed loop control system. For the following course, we will follow this order and explain the open loop system and the closed loop system. But at this time, you just need to have a rough concept about these two terms. As for the details, I will explain to you in further classes. Let's first take a look at the part between the input and the controller. And this course's unit will all be about this part between the input and controller. Let's first practice a topic, which is the control of the LED on and off lighting. During last class, we used the delay command to control the LED's on and off lighting, using the delay command's time length to change the delay's frequency to cause changes in the lighting state. For today's class, we will be using the input, that is, we will find a sensor and then use this sensor as a switch to control the LED's on and off lighting states. Let's take a look at this. These are the blocks commands that we will be using later. During last class, we used the digital pin setup, which is for the output part. For today's class, we will be using digital pin. If you move the mouse onto the blocks, when placing it on top, a description will show. Its description shows the reading of the digital pin. It will read the data and transfer it to the controller through the pin. This belongs to the input part. The digital pin is the input of the controller. We said that we take a sensor and use it as a switch. The sensor that we are going to use is called an infrared sensor. The infrared detector's more complete name is called the infrared tracing sensor. We will be using it for the following courses as a tracer. But in the beginning of our use, we will use it as a switch. Let's first explain how to use the infrared sensor and what is its principle of work. As the name suggests, it emits infrared rays. The infrared ray's color spectrum cannot be seen by the human eye, and is called infrared ray. These two things that look like LEDs, one of them will emit an infrared ray. When emitted, if it encounters an obstacle, it will be reflected. This reflection will be related to the obstacle's reflectivity. For example, if it is white, it will reflect more light. If it is black, it will absorb part of the light. So the infrared ray will receive less amounts of light. Therefore, through this reflection effect, with different light reflectivity, different readings can be obtained. At this time, this method that we explained was more about the infrared rays. Okay, let's take a look at which sensor we're going to use as a switch. We are choosing this infrared tracing sensor. This infrared tracing sensor will be used in an autonomous vehicle in later courses. In order to understand it first, we will use it in earlier classes as a switch. First, let's explain how this infrared tracing sensor is used. There are two things that look like LEDs. One of them is responsible for emitting infrared rays, and the other one is responsible for receiving infrared rays. When one of them emits infrared rays and encounters obstacles and reflects back, the amount reflected is related to the reflectivity of the obstacle. So if it is white, its ability to reflect light will be better. So the amount of light received will be greater. If it is black, since black absorbs light, its reflectivity will be worse. Through the obstacle's difference in color and reflectivity, the reception will also be different. This is how the infrared tracing sensor is used. In today's class, we will be using it as a switch, so when you approach your hand to it, because there is reflection, it will obtain a reading. When you take away your hand, after the ray is emitted, there is nothing to reflect upon, so this infrared receiver will receive no light. So it can read two different state readings. We can use this condition as a switch. Okay, let's first take a look after understanding the principle. Next, we'll see how to connect the wiring. Before writing the code, we must know how to do the wiring, because our electronic parts must be connected onto the controller. The first thing to do is to connect the wires. Let me tell you some concepts before connecting the wires. First, as long as it is an electronic board, electricity is required. Without it, it won't work. Second, even if there is electricity, the second thing is that it needs a load that is not connected directly out to the power source and back. This is called short circuit. So a power supply must be arranged with a load. Having a load, there will be wiring between the two objects to form a loop and the current will be conducted. When we are doing the wiring, later in class, the power supply connected will have a positive and a negative terminal. The electricity will come out of the positive terminal, pass through a load, then from the load it goes back to the power supply. It will be in a conductive state. This infrared sensor that we are going to use next needs to be connected first. Let's take a look at what's written on the board. It has a total of 4 connectors. As we said before, power needs to be sourced to this. At this time, this infrared sensor module will be seen as a load, so it needs to be powered by a power supply. The 2 power supply connectors are VCC and GND, which are responsible for power reception. This is a sensor module. It will have signals that needs to be transmitted to our controller, so it must have connectors. This infrared sensor that we chose is special in the sense that it has 2 sets of outputs, one of which is DO, which is the digital output connector. The other one is AO, which is the analog output. So it has 2 outputs. Of course, when we are using it in the beginning, we will use the digital part. However, we will be doing the wiring for both at the same time. When we use it later, because wiring with the Node MCU is a bit inconvenient, for the following class, we will use an expansion board called the Motor Control Shield. As the name implies, this expansion board has another wider application which is to be used to drive a motor. Regarding this board's details, we'll talk about it later. We will first use these connector pins. I would explain about these pins first. There are 3 rows in total. The orange row that I drew belongs to the signal terminal. So you can see that there is a 0 here, so that it is the D0 pin. The one with the 1 is called D1, then D2, D3, D4, D5, D6, and so on. This row is in charge of the I/O connection. So in our last class, we mentioned a GPIO, which is used for universal input and output. This whole row is responsible for that. Down here, we will connect the power supply's positive and negative terminals. This whole row is for positive electricity, and this row is the connection to ground. In this course, we can see that this infrared sensor's VCC and GND will connect straight to the power supply and the negative terminal, which is the connection to ground. For the other signal terminal, we would choose the D6 terminal to connect to it. By the way, for the expansion board, let me remind you one thing. When connecting to this expansion board pins, students may accidentally bump them, causing the pins to get skewed. So normally these pins should be perpendicularly upwards, and each pin do not contact with each other. So if you find out that the connector pins on your motor control shield are skewed, two of the pins are accidentally in contact, then you can use pliers to slightly adjust them correctly. For this motor control shield, we can take a look at the D0 connector pin, which is the pin under the 0. This one is a bit skewed, so you can use pliers to straighten it. If we want to use the motor control shield, we still need to combine it with the controller board. So later I will ask you to take out the control board, this Node MCU controller board. We are going to combine them together. When we installing it, pay attention to these two parts that look like antenna symbols. They need to correspond with each other, so when these pins are combined, these two antennas are on the same side. When inserting the motor control shield, beware, the Node MCU board and the motor control shield need to be parallel to each other. It needs to be inserted in parallel. If they are not parallel, it will get stuck halfway. If it gets stuck, by no means try to push it down forcefully. It needs to be pulled out again and then inserted again. When doing so, check that it is leveled. This is the correct way. After introducing the expansion board, we're going to do the wiring next. Why are we using the expansion board? Because when using these sensor modules, they must be additionally powered. For additional power, if we use the Node MCU board only, there are not many positive and negative terminals. So we are not able to externally connect many sensor modules. That's why I need this kind of expansion board, so that we can connect positive and negative terminals separately. So it will be more convenient when we connect the wires later. This is the first thing. Secondly, let me remind you of an important concept when you are doing the wiring. If you want to do any wiring, the power supply must be cut off. You must do the wiring when there is no power. During this process, please do not be lazy. Many of you may think that it is okay, it is just for a moment. However, it only takes that one moment when the positive and negative terminals accidentally get in contact. It will short circuit, and the circuit board will be burnt out, so please pay attention. Because this kind of board is not used correctly, it actually gets burnt out easily, since it does not have additional protection mechanisms. When using it, you must follow certain rules. First, if you are going to do the wiring, please ensure that the power is cut off. Let's have a look at this. The infrared sensor has 4 connectors. We have VCC and GND. As mentioned earlier, VCC is connected to the middle row, which belongs to the power supply. GND is connected to the outermost row, which is the connection to ground. Next, there is a DO, digital output pin, which will be connected to the D6 pin. There is an AO in the far end. This AO connector pin should originally be connected to AO. However, this motor control shield underwent special processing, which will be explained later on. Please do not connect it to AO. Connect it to AB instead, which is closer to the inner side and not the AO on the outer side. We will explain it later. We will first connect the wires. After connecting everything, you can try and do this first. Please make sure that the power is cut off. Do not do any wiring when the power is not cut off. I will give you some time. Once you're finished, before you power it, please pay attention to one thing. Once you're done with the wiring, please make sure you have checked whether the wiring is correct. I'm not asking you to confirm it 3 times. Why? Because if your thinking is wrong, checking 3 times will still be wrong, so you need to find 3 people to check for you whether there is any error in your wiring. Why do we need to do this? Because the wrong wiring will cause burnout. So please be extremely careful when it comes to power. Otherwise, no amount of boards will be enough, so be careful and ask 3 classmates to check for you. After we are finished with the wiring, let's visually check if the hardware wiring is complete. Once finished, the next thing is to check if the signal can be read by the Node MCU. We are going to do the following action. The infrared sensors are connected to the Node MCU through a DuPont line. We will transfer the data read by the Node MCU to the computer. We transfer the data to the computer through sequential signals so that it can be displayed and shown to us. Let's go to the desktop and open the Arduino folder that we previously downloaded. Open the folder and click on this Arduino program. It takes a bit of time for the program to run, so let's wait for a bit. I mentioned before that you can do writing type programming in Arduino, as seen here. However, we will use this for the Arduino IDE's Ardu block. When using it, we found out through experience that sometimes it does not run normally. So we suggest that you do not perform any operation in here. We will only be using its blocks. We select Ardu block ESP and open it. Let's maximize the window for a better look. Let's take a look at this. Let's reopen the commands. We are going to transfer the data from the Node MCU, so we need a communication command. Select this serial println and place it here. As mentioned earlier, the wiring is connected to the digital pin D6, so we'll drag out the digital pin block and select D6. Click on this inverted triangle and select the D6 pin. Next, we are going to combine them. But you'll see that it cannot be done. Why? That is because its shape is different, so we need an adapter. So let's go to the communication group to find one that has the same shape. Let's choose an adapter and place it in. After it's done, let's take a look at this. I have this assembled and we need to upload the data. Let's look at it separately. We'll display it side by side to look at the process more conveniently. Remember that when you're planning to upload the data into the Node MCU, your USB must be connected. Let me show you. An incorrect demonstration. Let's go to Tools and select Serial Port. As you can see, if we haven't made any connection, this will be reversed out and there are no COM ports shown, which means no connection was made. I'll plug in the USB. And click again on Tools. And a serial port number will appear. COM3, which means that a connection was made. When you're done, you can check the lower right corner of the Arduino IDE. It will show the status, the board serial number and the COM port number connected. All will be shown here. Next, upload the data. When uploading, it will ask you to save the file. The file saved is an Arduino file called an .ini file format, which is not the same as the Arduino block file. So if you like using this program, remember that if you want to keep this code, you must save the file in the Arduino block ESP environment. Once the upload is done, we'll use the serial monitor to read the state. You will see a message 1. Let's bring out this visualizer and compare. When my hand approaches the infrared sensor, there will be a reading of 0. When I let go, the reading becomes 1. Okay, through this state, we can determine whether our hand approaches the infrared sensor. Try to do the wiring and upload the program. And see if your Node MCU signal can be uploaded to the Node MCU. Give it a try. Once you have finished with the program upload, let's have a review. During the operation process, when we get a reflection signal from an approaching object, what is the reading for D0? Do you remember? Yes, it is 0. When my finger is taken away, there will be no reflection and the D0 value is 1. We are going to use these two readings for the upcoming program and see how to do the assertion and work. Suppose that the result that you get during this process is different. Maybe it doesn't even have a reaction. How do we deal with this? Actually, during this kind of robotics course, it is very important to do a simple debugging task because you need to be able to correct certain errors yourself. How do you deal with this? What do we do? Let me tell you a simple method called the A/B test. What is the A/B test? We mentioned it in our previous class, so let's have a review. First, let's bring out this wiring diagram and take a look at it. How many segments do we have in total? It has the sensor, the signal data from the sensor, which is transferred to the Node MCU through a DuPont line, the Node MCU which transfers data to the computer via USB. For the A/B test, what should we do? We will look for a classmate who got the right result with his parts. Ours is wrong, but we don't know which part is wrong, so we'll exchange the parts one by one and test it out. For example, we start with changing the infrared sensor, then change the DuPont line, then the Node MCU one by one. Even though this method is a bit stupid, but in reality, this method is often used when working with electronic components because it can be done quickly. Of course, is there any other method other than exchanging parts? Yes, there is. There is another method, which is by testing the electronic board. We'll use digital multimeter. We can take a look at this digital multimeter. There are two most common ways of using it. The first one is to measure the voltage. The Node MCU's voltage is 3.3 volts, so we can set the multimeter to the direct current voltage 20. When doing this, let me remind you that you must ensure that the probe is connected in the right place. The red probe must be connected to the voltage current resistance jack. The black probe will be connected to a joint jack. Multimeters usually have another jack used to measure large currents. This is usually not used because the voltage we mostly measure is more commonly used. Once the setting and wiring are both correct, we are going to place the probes on the infrared sensor's positive and negative terminals, then measure it with the power on, and see if a voltage value can be measured. According to the PowerPoint slide, this means that it is powered. The power supply is providing electricity normally. When the power supply is powering the infrared sensor, it means that the electricity is normal. Then we can conclude the power supply is working normally. What could be next? The signal may not be passing through. If the signal is not passing through, how do we measure it? At this time, we'll switch the multimeter setting to ohm to check whether the conducting wire is connecting or not. We usually use the ohm setup, so you can switch the multimeter to the ohm setup, to the one with the smallest value, because it also shows the buzzer sign. What does the buzzer sign mean? In case of short circuit, the buzzer will make a sound. You need to pay attention to one thing, that this time please make sure you cut off the power. Why? Because when measuring the ohm, there should be no power running, so please cut off the power. At this time, the resistance does not have a positive and negative polarity. You can directly place one of the probes at the digital output, and the other one can be placed directly at the D6 connector pin. Because at this time, you cannot measure the motor control shield. You can only measure D6 on the Node MCU. Check the D6 connector pin, which is the position of the red probe, and see if it is possible to hear a short circuit sound, which will mean that these two probes are connected. We can use this method to confirm if the signal is passing through. This is the test method for hardware wiring. We have already confirmed whether the infrared sensor module signal can be sent to the Node MCU. We can move on to the next segment, which is to use it as a switch to control the LED on and off lighting. Let's take a look at this slide and review this again. Our input is the infrared sensor. Its signal has already been transmitted to the controller. We have confirmed this using the computer. Next, we need to transmit this signal to the controller for assertion. After that, we can then perform the digital write, which is the digital output part to control the LED's lighting. We will be discussing the new segment of today's class. We are going to make a selection structure. We will be doing an if statement. Before doing it, let's first explain the process. There will be a condition for the if statement. We will evaluate it. If the condition is met, we go to the true side. If it doesn't, then it's false, and we execute the false side. The Ardu blocks looks like this. It will first state a condition to be met. If it is true, it will execute the then execute part. If it is false, then it will jump to the otherwise execute part. This is the writing code for it. Next, we'll perform the assertion of the statement using the D6 pin. If you have learned about C language, you may wonder, why is it that inside the condition, there is no comparison statement? such as larger than or smaller than. Why is the digital pin placed inside directly? This is what's special about it. In our digital board, there will be a data type called Boolean when performing controller-related tasks. Our digital state is actually a Boolean data form. Why? Because it has only two states, 0 and 1. The digital pin only has 0 and 1 is actually a data type. We will talk more about this data type in upcoming classes. For now, we can first establish this concept. The reading obtained by the digital pin is 0 and 1. Boolean data form. Within the Boolean data form, the 0 represents false. In digital signaling, it also represents low voltage. If it is 1, it represents true, which means that the condition is met, or high voltage in digital signaling. Let's review this part. When evaluating the if statement, if it is true, it will execute the then execute section. If it is false, it will execute the otherwise execute section. Since the data read from the digital pin is a kind of Boolean, so when it's 0, it means that it is false, and it will execute the otherwise execute section. If the value read by digital data is 1, it represents true and it will execute this section. When using it in this context, we will frequently use the data read by the digital pin to determine if it is a 0 or a 1, which at the same time represents false or true. Next, let's take a look at this. We're going to start adding in the things we've observed into the program selection structure. At the beginning, we first read the sensor's data. When reading the data of our hand approaching the sensor, it will sense that there is an obstacle present. When there is an obstacle, the data we obtain is 0, and it will perform the turn on light task. I would like to remind you that within the Node MCU, this is considered a low state task. If you want to turn on the light, you will have to output low for the light to turn on. On the other hand, when we move our hand aside, you will find that the data read is 1. At this time, it will perform the turn off lights task. When we are performing the if statement, we will evaluate the digital pin by checking the data obtained by the D6 pin. For the true statement, we will turn off the light. In this line, since 1 represents true, when the hand is removed, the light will be turned off. You can see that the D6 pin corresponds to the D4 pin setup and is set to high, which means to turn off the light, because it is a low state task. If it is a 0, it means false, and it will turn on the light, because when the hand approaches, the reading is 0. So in the Boolean data form, it means false and it will turn on the light. For that, we'll set the low state task to high. The program is as such. You can try it out yourselves. For the section between the infrared sensor to the node MCU, we use the digital signal. Next, we are going to introduce the analog signal. At the same time, we are going to spend some time to explain how circuitry works. As we go through these sections, we will help students review some simple basic electrical concepts so it will become easier to explain upcoming circuitries. First is the Ohm's law. Let's take a look at Ohm's law. The first thing is this diagram. When drawing this diagram, the diagram on the left and the diagram on the right are actually the same. But when we are drawing, we sometimes omit the VCC as well as the positive and negative terminal lines. Why do we omit them? Because sometimes in circuitry, if there are many power supplies that need to be drawn simultaneously, it will be a bit messy, so we are used to drawing it this way. But actually, this represents the battery positive terminal and the negative terminal, but they are actually connected. I wanted to clear things up about this circuitry. Ohm's law is represented by this formula, V equals I times R. What does it mean? The voltage between the two ends of a conductor will be proportional to the current flowing through. This R is their ratio coefficient. This is called the Ohm's law. This is the first concept. The second concept is this. If there are two terms, the first one is power supply. For example, this supplies the voltage for this circuitry to work normally. We call this power supply. There will be a voltage drop at R. When the current flows through the resistor, there will also be a VR equals IR. This VR is called voltage drop. So there are two terms. VCC is the power supply's voltage. There will be a voltage drop at R. When the current flows through, it will cause a voltage difference at the resistor. We call this voltage drop. Next, let's take a look at the second diagram. The second diagram is called the voltage divider circuit. This voltage divider circuit will often appear in our upcoming lessons. What is a voltage divider circuit? These two diagrams are actually the same. We draw it this way for you to familiarize with it. VCC represents the battery's positive terminal and ground represents the negative terminal. They are actually connected. This R2 is a resistor. R1 includes an arrow, which means it can be adjusted, so it is called a variable resistor. Let's take a look at this circuit. In a circuit that is connected in series, the current remains constant. The voltage drop generated in R2 will be equal to I times R2. The voltage drop generated at R1 will be equal to I times R1. The voltage drop generated by these two resistors are VR1 and VR2, which will be equal to I times R1 and I times R2. Since I is constant, we can remove I from the equation and obtain R1 equals R2. In a circuit in series, the voltage drop of the two resistors will be proportional to their resistance value. What does this mean? When the resistance over here increases, R1's resistance becomes larger, which means that the voltage drop partition to it will be larger. As this is smaller, R1 becomes smaller, and the voltage drop partitions will be smaller. This circuit will be seen very often in our upcoming discussions, so I'll first explain to you the concept of a voltage divider circuit. Next, let's take a look at this. We will talk about the sensor. We will be using a simpler sensor, which is the photoresistor. The photoresistor will change its resistance value according to the light reflected. This one over here, it is a resistor with two arrows pointing towards it, which means it's been illuminated. The photoresistor will change its resistance value according to the light's intensity. The stronger the light, its resistance value becomes smaller. The dimmer the light, its resistance value becomes larger. Through this voltage divider circuit, you can see that when light illuminates it, the voltage drop in this voltage divider circuit will vary based on the change in the resistance value. So you will get a variable voltage. This variable voltage is called an analog signal due to its constant changes. In our previous lessons, we often heard about digital signal. Digital signal means we will send the analog signal to a voltage comparator for comparison. This voltage comparator will set a voltage value, which will be compared with our analog signal. Whenever it is greater than the reference value, we will see it as positive. If it is lower than the reference value, then it is negative. This is how we convert into digital signal. After it passes through a voltage comparator, it will be converted into digital signal and then sent into the node MCU. In our last lesson, we talked about digital signal entering the node MCU. Our analog signal, we can also be sent to the node MCU, but it requires an action called ADC. What is ADC? It means analog to digital converter, which converts analog signal into digital signal. It will have a mechanism. The node MCU only has one pin to perform this action, which is the A0 pin, which we will explain more about this as well as how to convert it. After talking about photoresistors, next we're going to talk about the infrared sensor module. The model number for the infrared sensor that we are using now is TCRT5000. Let's take a look at the circuit. I have simplified the circuit by showing these few key components to explain it. Let's take a look at this. There's an infrared light emitting diode and a phototransistor. The infrared transmitter will emit an infrared light. When it hits the wall or an obstacle, it will reflect back. Then the photoresistor will change its state based on the intensity of the infrared ray. When its state changes, it will affect the voltage output over here. The output before going through the comparator will be seen as an analog signal because of its continuous change. After going through the comparator to compare the voltage value, we can obtain a digital signal. This digital signal can be sent to the node MCU to be used. This is a macroscopic circuit mode. Let's have a look at the following module to dissect it into two parts. When the infrared transmitter emits an infrared ray and it hits the wall, it will reflect back to this phototransistor. When reflecting into this phototransistor, what will happen? You can imagine this phototransistor as a faucet. This pin over here that was left unused is the faucet's valve. The more light there is, the more open my valve gets and the more current flows. The brightness of the infrared ray reflected back will determine the current that passes through this phototransistor. For the third step, we can come to a conclusion. As light increases, the current will also increase. The less light is reflected, the current that flows through will decrease. So the voltage at V can be calculated using a circuit. V will be equal to VCC, which is the power supply voltage minus the voltage that passes through R2. I times R2, which solves for the voltage V. So looking at it from the mathematical formula, as light increases, current increases. What will this cause? VCC is fixed. R2 is also fixed. What happens with V? It will get smaller. When my infrared sensor deals with something with higher reflectivity, such as something white, V will get a very low voltage value. If it is black, what will happen? When it's black, the opposite will happen, because black's reflectivity is very low, so the sensor will barely detect any light. If light cannot be detected, the current will drop. If the current drops, VO will be almost equal to VCC, so it will get a larger voltage value. Later we can verify whether our reading is the same as our circuit analysis. The reading will be an analog signal. We will look at the digital signal next. It will connect to this comparator over here, which is an operational amplifier. We can imagine it as a component that compares the voltage. There is a variable resistor symbol here. There is also a variable resistor knob on the infrared sensor. What is this for? We can adjust this variable resistor, which will work as a voltage divider circuit and divide it into two resistance values in series. We can change the VR state and obtain different voltages. Adjusting this variable resistor knob, you can change the voltage distribution and modify the reference voltage's value. When this is set to half, the voltage obtained over here will be half of VCC. We use this value as reference for comparison. When the analog reading from the infrared sensor exceeds half of VCC and has a larger value, what does it mean? It means it's positive, so it gets a high voltage. If the reading obtained from the phototransistor's output voltage is smaller than half of VCC, having a smaller value means it will obtain a zero reading. When the voltage over here is larger, the output system's positive voltage gets a high. If the negative value is larger, then we will get a negative output voltage instead of a positive one. We get high and low variations. Let's review again about the variable resistor, this one on the circuit. We can adjust this variable resistor to determine the negative terminal voltage to compare. What is this for? We can determine how white or how black the object needs to be for the system to output 1 or 0. You can slightly see two LED lights. One of them represents the power supply light. It means that when VCC and GND are electrically connected, this light will turn on. The other light is called switch indicator. What does it mean? When a reflective object is present, it will light up. When there is a reflective object and the output is low, this will light up. When does this light up? It can be adjusted through this variable resistor. Hello everyone. In our next class, we are going to make an oscilloscope. Why do we have this lesson arranged? Because in our previous lesson, we talked a lot about digital and analog signals. What is the shape of these waves? We want to use the node MCU's function to draw it out. Let's have a look here. We are able to feedback readings. But can we see wave profiles that look like these? Of course we can. So for our next lesson, we will teach you how to draw digital and analog wave profiles. Okay, let's see how to use the node MCU to make an oscillator. The main function that we are going to use is in Tools. There is a serial plotter. We will draw the model through this serial plotter. How do we draw it? First of all, these are some signals that had already been read. We can put them on the side. We only need to read in the D6 connector pin. We'll put this serial println back. In the communication group, we can scroll down and find the serial plotter function. We'll choose channel 1, so we move the digital pin there, but you'll see that the adapter was put away. So you need to go back to the communication group and find a suitable adapter. And place it back. This way we can call out D6 wave pattern. Let's upload it. When uploading, the Arduino IDE will compile and upload. It requires some time, so we'll wait. It's done uploading. Let's bring out this window to display what we are doing. In the same manner, we select the serial plotter under the Tools menu. This time, we don't show these windows in series. Let's have a look. At this time, my hand is not approaching, it is shown a straight line, which still has a reading. Now approach my hand, then let go. At this time, the reading is 1. When my hand approaches, the reading is 0. Let go, and it's 1. When there is no obstacle to reflect on, the reading it gets is 1. When my hand approaches, it is 0 and you can see the wave pattern. When you move your hand, you will see what is known as digital wave pattern. It is either high or low, and it does not have any values in between. You can try out this part yourselves. The next topic we're going to talk about is digital and voltage systems. When you were trying this out, did you notice that the signal that you saw varied between 0 and 1 was not an actual voltage? An oscillator actually displays the voltage variation. Why? The reason is because the Node MCU is like a computer. It uses binary to store its calculating data. The data running within the Node MCU is all binary, so it will only show 0 and 1. We can think this way. Within the Node MCU system, the high and low are 1 and 0. In fact, they are the same as the system's 3.3 volts and 0 volt. If you look at it from the voltage perspective, high corresponds to 3.3 volts and low corresponds to 0 volt. Next, how can we see the real wave pattern? The real wave pattern should look like this. It is an up and down variation, but the voltage value shown should be 3.3 volts to be high and 0 volts to be low. So next we're going to make use of another function called map. We'll use map to make a function variation. What is this map function for? Let's have a look at this example. It will take the numbers from 0 to 1 that is, low to high values, then map them to another value range, in which 0 and 1 will become 0 volt and 3.3 volts. Let's go over it for real one time for you to see. Let's open ArduBlock ESP and select the map function. The map function is a mathematical operation, so we'll click on this and drag it out. After dragging it out, we'll place this on, which are the readings for 1, and place it in channel 1. Its value is 0 to 1, so we'll input 0 to 1. And here, 3.3 volts, then press enter. Then click upload. We'll change the original 0 and 1 variation to a 0 to 3.3 volts mapping. Once we are done, we'll select the serial plotter. Suppose that my hand approaches the sensor, then you can see the number variation. You will see that the value will be larger than the 0 and 1 previously shown. It has reached 3.3 volts. In reality, this is not actually 3.3 volts. We will solve this problem later on. You can practice mapping your own function using this map function. You can give it a try yourselves. The next topic we're going to talk about is the analog input, A0 and AD. First, let's have a look at the infrared tracing sensor's analog output. The analog signal is sent to the node MCU to be used. The first step is to digitalize it. Inside the node MCU, we need to convert these analog signals into digital signals. You can think of this conversion method as what we did earlier with the comparator. It's just that the comparator's range is larger. The original 0 and 1 comparison will be converted to 0 to 1024 comparison. So if our input voltage is from 0 volt to 3.3 volts, it will be converted to a larger range, 0 to 1024. So this action is known as analog to digital converter, which is an ADC conversion method. So you can imagine it this way. If it's 1.6 volts, you can define how much is the analog output. If it is 1.65 volts, the digital reading it corresponds to should be 512. First, let's take a look at the analog input connection method. As said in an earlier lesson, I asked you to connect the infrared sensor's AO to the AD connector pin instead of A0. A0 is directly connected to this part of the node MCU. Why not connect it like this? Why not connect it to A0? The reason is, because the node MCU's ADC conversion range is only from 0 to 1 volt. However, our infrared sensor's supply voltage is 3.3 volts. So the signal range that can be read is also between 3.3 volts and 0 volt. Originally having a range between 0 and 1 is too small. So, through this kind of voltage divider circuit to amplify the signal's read, so that all 3.3 volts can be read instead of just reading up to 1 volt. So we'll do a simple voltage divider circuit. This is the reason why we connect it to here instead of AO. We want to read it through the AD pin. Next, let's take a look at the analog reading required to read the infrared sensor. Let's see how we do this. We need to bring out the analog pin block. There will be an analog pin block here. When you move the cursor onto it and leave it on the arrow for a little bit, it will display the description, read pin's analog value. So we are going to read this analog value. This is A0. In the node MCU, the only pin that can read analog is this A0 pin. We will bring out the serial println to use. This one. Then we connect this pin. When connecting this pin, it needs an adapter. So we'll use this adapter for it. From our previous work, we found that message will be followed by the signal. It does not look quite right. We can give it an equal sign and then perform an upload action. Once the upload is finished, the next step is to open the serial monitor. It will show a message saying cannot be used when serial plotter is open, because they both use sequence symbols. So let's close this window first. Then, open the serial monitor again. We'll show you an incorrect demonstration. It shows the message serial monitor cannot be used when serial plotter is opened. This time you can run it. When my hand doesn't approach the sensor, we get a 1024 reading. When I approach my hand, the reading will get smaller. You can try out this part for yourselves. After trying it out, let's have a look at this COM3 serial monitor's values. Its values changes between 100 something to 1024. The number it corresponds to is not too low. Why? Because of what it reflects. Let's go back and check the circuit. This is the circuit from which we obtained the analog reading. If there is a reflection, it won't be 0. The reason is because there's still a bit of voltage drop here, and it will not short circuit, since it is an electronic component. However, if it reaches 1024, what will be its status? There's almost no reflection, that is, when your hand is removed, you'll get 1024. Why? Because the light over here basically doesn't come over, and the phototransistor does not receive any light. It will be as if the faucet is completely closed off. This resistance value becomes infinite. When the resistance is infinitely large, the voltage VO equals to I times R, and the voltage value will be immense. So 1024 means that all the VCC voltage drop occurs at VO. After looking at the circuit analysis and reviewing it, we can know that this reading cannot be 0. A slight voltage drop will happen, but it will be close to 0. This is its value variation. Let's move on. Of course, when executing it, you will see that it runs very fast. You may ask if we can make it slower. Yes, we can. We give it a delay so that the program doesn't run so fast. Okay, next let's have a look at this. What we obtain is a number variation corresponding to 3.3 volts to 0 volt. We use the 1024 method to compare the number. 3.3 volts corresponds to the 1024 analog reading. Can we convert it to the actual voltage value? Of course we can. It's done in the same way as we did with digitalization by using map function to read it. Let me show you a demonstration. Let's work with this. We'll use the map function to do the mapping. We'll drag this portion to here. From the initial 1024, we need to map it to 3.3 volts. Press enter. Then drag this into here. Let's upload it. Once it's uploaded, it will be mapped to an actual voltage value. But this time, we will show the map function. This map function actually has a drawback. What is its drawback? We'll look at it later. The upload is finished. We will open the serial monitor to have a look. You see, the message changes to 3, 2, 1, 2, 3. Because it changes rapidly, so it will only change to 1, 2, 3, and there are no decimal points. There is no decimal point in the map function. This is an issue. If we want to show decimal points, what do? Okay, we just found out that the map function can only process integers and we can't get a more precise voltage value, so we can try to write a conversion function manually. Since we need to perform some calculations, we need to start using the concept of variable declaration. The variable can be seen as an unknown number, which will be stored in the node MCU to do calculations. We have to tell the node MCU board about what kind of variable type I'm storing in right now. But for different types, not only they have different properties, but the storage space required is also different. What we are showing here are 4 common types of variable declaration methods. Of course, there are others, but we will only talk about the ones we will use. If we end up using other types later, we will provide additional explanation. The first one is integer. The second one is unsigned long. The difference between these two is that the unsigned long does not have positive and negative numbers. It is a long integer, so it can store a larger amount of data. The next one is decimal. It is a variable for decimals, so it has decimals. For the integer or unsigned long kind of variables, they don't have decimals, so they don't have calculation for the decimal portion. So when using the map function, it will have this calculation issue. When the data type is different, the calculation range will be limited. Finally, the last type of variable declaration is the Boolean variable that we mentioned before. It only has two states, false and true. That is, variation between 0 and 1, which is only about the data form. When using the integer variable, we can declare a variable name. Of course, for the naming, you can choose a cooler name. But if you want to consider that future programs will get much larger, I suggest that you pay attention when declaring the variable name and don't name them randomly because with more names you will tend to forget. I suggest that you use the Camelcase naming method. The first word is always lowercase. For the second word, the first letter is written in uppercase. For example, first name. The N can be written in uppercase to distinguish it. If you need to use two words as variables, you can use this method. Variable declaration written all together with no spaces can be done this way. First, let's see how we write this conversion function. Value is the analog pin reading that we measured. The actual analog value measured from the A0 pin, we will name it value A. This value A corresponds to the analog value of 1024, which is equal to 3.3 volts peak voltage. Since it is a ratio function, our actual voltage will be equal to value A times 3.3 divided by 1024. We can write it this way. Let me show you a demonstration. The first variable declaration is the set integer. We can type in a name. Value A. This value is measured from our pin. We connect an analog pin. Ours is the A0 pin. Next, we need a communication. That is the serial println, which is the signal sent out. At message, we add an equal symbol. This way, it's easier to identify. Next, we will perform a simple calculation. We can call it out. And first of all, we need to multiply value by 3.3. Copy value. Here we need to pay attention. Let's have a look at variables and constants. You can see it here. We can drag this out. You can see that for this variable name and value, this is a constant. The color for value is lighter, and the color for the variable name is darker. You need to have this clear because some students often make mistakes. If it is a variable name, it's darker colored, while the value is lighter colored. So you have to pay attention to this. I'll put it back. So we want to multiply value by 3.3. Then we divide it by 1024. So we drag this out from the mathematical operation group. If you drag out the wrong one, it is alright. Click on the inverted triangle to adjust it. We put this in. Next, from the variable group, we can grab a constant to use, or we can directly use copy. Then we type in the value, 1024, and press enter. The result of this calculation is placed here. And remember to add an adapter here. I dragged the wrong one. Be careful when dragging. We combine them to prevent it from running too fast, so we will add a delay between them to make it run slower. Then we upload it. Once the upload is completed, we can look at the serial monitor. We can operate it using our finger as an obstacle to move it on top of the infrared sensor. And you will find out that it can read a signal value with decimal point. It can be converted into a real voltage value. We can try and write a simple conversion function. You can try it out yourselves. Once we're done, let's move forward and look at the wave pattern. Once we obtain the readings, we can plot the wave patterns. Let's first show a case where a mistake was made, using map to convert to real voltage value. We can have a look at this. There's no need for you to practice this part because we've already done part of it. Next, we can look at the results. You see that it can only show integers. That is because map can only process integer values. So next I will ask you that for the next step that you need to practice. Since we already know how to process analog readings, we've already practiced with analog values. Now I ask you to use this D6 pin to perform the conversion. Using the D6 pin is actually not hard because this D6 pin is a digital pin. There are only two variations for a digital pin, which is 0 and 1, so we just need to multiply this by 3.3 to know that if it is 0, then it's 0. If it is 1, then multiplied by 3.3 and there's no problem. For the result of its execution, you can try it out yourselves. After you've tried this program, we can look at the next slide. The wave pattern will look like this. This is more normal. It is a wave pattern with continuous variation. It will not be as serrated as before. This is the most important part for all these classes we've had so far, which is this voltage oscilloscope. We can see that the red line represents the analog reading. It is a new value with continuous variation. The blue line is the digital reading, so the value only varies between 0 and 1. After we are finished practicing this, we can see a real oscilloscope. In fact, the reason for you to have this class is not just to see this voltage pattern. If there are similar methods for measuring values in the future, you can do it through reading the variables and then present them in the form of wave patterns, which is easier for you to observe the curve variation of these variable changes. This is a very useful tool. Once we are done, let's review. The signals obtained from the digital and analog pins represent the values of a digital system, and not a real voltage value. You have to use map function or other conversion functions to obtain the real voltage value, which is the real voltage value that we measure using the multimeter. The last thing to review is this, because we will be using the infrared sensors very frequently. You should understand this part clearly. When the infrared sensor senses the color black, the digital signal read is 1. When it's white, is 0. In analog terms, black is 1024, while white is around 100 or less. For a middle value, between white and black, then you see what value it is. You will see its changes. These changes are the results of the readings obtained by the reflection of the infrared light. Also, when using the infrared sensor, the background light can also affect the readings. So when we use this thing, there will be other details that I will explain to you. Hello everyone. What we are going to perform today is analog input, control, and digital output. When going through this lesson, let's have a review about variables. What is a variable? It is a location which can later store known and unknown data. This data may be numbers or words. There are different variable types. We have a space to remember this data, and there may be different variable types. What we are doing for practice is an easy integer variable, so this variable is just the integer part. Secondly, when declaring variables, we will give them a variable name. For the naming of the variables, we recommend paying attention to it. It cannot be too simple. Why? Once the program becomes very long, you may have many variables and end up forgetting the reason for naming such variable. If you want to use words as variables, it's okay. As the number of variables becomes larger, we suggest that you use the Camelcase naming method. You may use two words combined together. The first word written in lowercase, and the first letter of the second word is in uppercase to make a distinction. This is called the Camelcase naming method. We suggest that you think about it or see which kind of variable declaration naming you prefer. Let's first take a look at the following. We need an analog reading to control the LED's on and off lighting. That's why we need to declare the analog reading as a variable, then use this variable. Next, we are going to explain this flowchart. Our topic is what we are going to use the infrared sensor as a switch. This switch will be made using the infrared sensor. When our finger approaches the infrared sensor, our LED will light up. When I take away my finger, the LED will turn off. This is what we will try to achieve, so we will use the analog input of an infrared sensor as a reading to determine the relationship between our finger and whether it is far or near. Let's recall our last lesson. We discussed that when our finger approaches the sensor, there will be a reflective object, so the reading will be low and go towards the value of 100. When my finger leaves, and there is no obstacle present, the reading will become large, close to 1024. So we'll set the reading condition to 700. So when the infrared sensor's analog value is greater than 700, it means that there is no obstacle present. My finger has already been removed. When my finger is removed, it is true. When it's true, we know that the LED light is turned off. When the LED light is off, our digital output is a low state action, so its output is high. Inversely speaking, when my finger approaches the infrared sensor, what will happen to my reading? It will be less than 700, so it does not meet the condition, so it's false. At this time, the LED light needs to turn off. It is a low state action, so we have to output low. So you can have a look at this program on the side. The first line declares the variable value IR. Value IR is the reading obtained from the infrared sensor A0. For the next line, serial println, why do we need to write this line? Because we need to make sure that the reading is sent to the computer. So in the beginning, you can form the habit that when a variable is read, you need to use serial println to check whether this value IR reading has been imported. Once it's imported, we use this value IR to evaluate. If it's larger than 700, then it's true and executes this section. We set the D4 pin to high. When it's high, the light should be in this state. Otherwise, we execute the false section. You can try it out yourselves. Now we can look at the execution results. When my finger is removed, the reading is 1024, which means there is no obstacle present, so the action we are executing is turning off the light. When my finger moves over, the reading value is less than 700, and the LED will perform the light up action. Hello everyone. What we will do next is the principle and use of the ultrasonic ranging sensor. Let's take a look at this. The principle of work of the ultrasonic ranging sensor. On top of the ultrasonic sensor, there is a component that emits ultrasonic waves. When the ultrasonic waves hit the wall or an obstacle, they will bounce back and be received by a receiver. During this emission and reception of the waves, a time difference can be calculated. After calculating the time difference, we can use the sound's traveling speed to calculate. Assuming a temperature of 20 degrees, the speed of the sound waves is around 343 meters per second. I can multiply this by the speed difference. Since it goes forth and then bounce back, I divide the time by 2, then multiply the value of the speed of sound of 343 by the time. Then we can calculate this distance. The ultrasonic ranging sensor uses this method to calculate the distance. Next, I will ask you to do the wiring. Likewise, we need to pay attention to the positive and negative terminals. We will take the trig TRIG and connect it to the D7 pin. Echo will be connected to the D8 pin. Likewise, wiring should not be done in the powered state. Power must be removed. It cannot be in a powered state. When the wiring is done, ask other classmates, at least 2 or 3 classmates, to help you do a final checking. Do not do everything on your own. This is very dangerous. Now we will bring out the ultrasonic sensor blocks from the generic hardware group and bring out the ultrasonic sensor. This trig pin is connected to D7. Echo is at D8. We select the correct pin. For the first step, we will set it up as an integer variable. We'll call it out from the variable group. We can give it a name. We'll combine them and we will name it value. VALUE and then distance. We will use the abbreviation DIS. Value distance. Okay, we'll print out this number value. We use serial println and call out the value distance and add an adapter. Then we upload it. First, let's check whether the reading value of our ultrasonic sensor is working normally. After that, we can go on. Once it's completed, this is our device with all the lines connected. We'll call out the serial monitor. Let's have a look. When our finger moves over, we will get a reading. The closer your hand gets, the lower this value becomes. Then we remove the hand. If there is nothing present on top, the value that is read will be the distance between the ultrasonic sensor and the ceiling. This ultrasonic sensor can work normally. You can try it out yourselves. After using your hand, to check that your ultrasonic sensor can work normally, we will move on to the next step. After confirming that our ultrasonic ranging sensor can read out values, it means that our ultrasonic sensor is working normally. Then we can continue writing our code. The topic we got was this. When my hand approaches to a distance less than 5 centimeters, the LED will light up. If the distance is more than 5 centimeters, the LED will turn off. So let's take a look at this flowchart. Our evaluation will be based on the ultrasonic sensor's readings. If it is greater than 5 centimeters, it's distant. So if this condition is met, the LED will be turned off. You can look at the code we've written. D4 is high because the LED performs a low state action, so having it written as high is correct. The other side is false. The condition is not met. The distance is less than 5 centimeters. The condition is to be larger than 5 centimeters and is false, which means it's less than 5 centimeters, so the LED will turn on. The light can be turned on, the low state action is set to low, so this code is written correctly. Let's try and finish this code. We will close this and come back here. We will use this. We can get this if else and use this value distance for assertion. Then we go to the test group. Here we need it to be larger than 5 centimeters. So we are missing a constant. Let's go back here and let me remind you that the number for variables and constants are different. We enter the value 5. After that, let's take a look. What we need to do is to set up the digital pin. We set the D4 pin to high. So when it is larger than 5, it's true means executing this section. On the contrary, if it does not meet the condition, it is smaller than 5 or is close to 5, we set it to low, so it can perform the light up action. Let's upload and see the results. Once the upload is complete, we can bring up our screen and see our device projection and check its actions. Okay, let's call out the serial monitor and make the window slightly smaller. Right now, it reads 25, so when my hand moves down closer to it, when the value gets below 5, it will light up. When the distance of my hand exceeds 5, such as right now, it reaches 6, the light will turn off. This is better than the infrared sensor in a way that it can be operated using a more quantifiable number. Okay, now it's your turn. You can try it out yourselves. Once you're done, let's look at the next part. What we are going to do next is to use the ultrasonic sensor to simulate the parking sensors of our home cars. We don't have a buzzer on it, so there's no sound. However, we can use the blinking of the lights to express the distance of the obstacles behind the parking sensors. The closer we get, the faster the light blinks, which is similar to the reaction done by our parking sensors. We'll use the LED lights blinking action to simulate the intermittent sound frequencies. Let's take a look at this parking sensor project. We have already completed the switch portion. Next, we will use this switch to further extend it. We will use the distance to determine the blinking of the LED. Let's take a look at this flowchart. The first half is the design of the ultrasound. We have done this before. We need to convert the distance to delay time, because there is a delay between the blinks. The greater the distance, the longer the delay time. This is the same as the parking sensor of our home cars. The closer we get, the faster it blinks, so we need to upload this program. An important part of this program is that we perform a mapping action in here. Our delay time is mapped to our distance. For the distance between 0 and 30, we convert it to the delay time of 50 to 2000, which is 2 seconds. That is 50 to 2000 milliseconds. When the distance is 0, our blinking speed is 50 milliseconds. And if the distance is 30 centimeters, our blinking delay time is 2000 milliseconds, which equals to 2 seconds. Let's upload it. Once the upload is completed, let's check our movement. Let's approach our hand to the sensor. We can see that the delay time is at 24 centimeters. Let's approach the hand. Six, 4, 3, 7, 6. You will notice that when my finger gets very close, why is there an abnormal reading? When my hand is far away, let's say it's a bit far away, the reading is more normal. Why? Let's explain why. In fact, this is an incorrect action, which is related to the execution of ultrasonic sensor. Let's take a look. The example above has two errors. The first error is that the ultrasonic ranging sensor has limited range. In our building block, it can only measure the distance between 2 and 300 centimeters. When it is less than 2 centimeters or more than 300 centimeters, it will send back false. An error will occur, so the values may have problems. This is the first error. The second error is the delay, which is a very annoying command. Why? Because delay means wait. If I wait 2 seconds, it means the distance is far. I give wait 1 or 2 seconds. During this interval, it does nothing else. When the distance is far, not only does it not blink, but the computing stops completely and it does not perform distance measurements. Within the delay interval, it will not perform any actions. So for this delay command, you need to pay attention when you are writing the program for the self-propelled vehicle and try not to use the delay command if possible. When making the corrections for this program, we did two things. The algorithm is pretty much the same, but we made two corrections. The first one was that our distance measurement is not set too far. Make the delay time shorter. We will change it to between 3 and 15. And the second correction is our delay time, that is for the 500 milliseconds. We don't make the delay too long. The second correction we made is to shorten the distance in value distance over here. It can only be in the range between larger than 2 and less than 16, which means it can only perform actions when it's between the distances of 3 and 15, because if the delay time is too long, having the ultrasonic sensor would do nothing. It has no meaning, so we need to prevent this error. Let's upload it and execute its results. It's done executing, so let's check its operation. We call out the readings for comparison and let my hand get close to it. It can only work when it's between 3 and 15. See, when you get closer, the blinking becomes faster. When you remove your hand, all readings are in a normal state. When the reading gets to more than 10, it is still normal. If the distance is too long and exceeds the range, it stops computing and it will light up the LED. The lighting up action is the last command after the delay is performed. That's all for today's lesson.